Okay, we're going to do this real quick, then we're going to go over any questions you may have, then we're going to jump right into it. So we've done this like at least twice before. The idea here is if you could change this into something with cosine squared, then your life is a little bit easier. And so you do this type of thing. This is the thing that you want to remember for the rest of your life, is that cosine squared can be written as 1/2 plus 1/2 cosine what?
Of 2x.
2x, right? Now, of course, there is another way that this is written. This is one way of doing it. In calculus, it will be to your benefit to write it like this. It may seem like a trivial thing. It's just slightly easier. If you have it the other way in your head, it'll also work. This is just slightly easier. So then we got to square this out, right? And so I'm going to go first outer, inner, last. That gives me a quarter. Outer gives me a quarter cosine 2x. Inner gives me a quarter cosine 2x for a total of 1/2 cosine 2x.
And then it's a fourth.
Then it's a fourth, but now we have this problem, is that this is not a first power cosine. And so we do the same trick again, right? And we say, so this is a quarter times, and then we go 1/2 plus
1/2 goes 4.
There we go. Right. It just doubles whatever's inside. And so we have a 4x. Now I'm just going to multiply this guy out, and we have an 1/8 plus an 1/8 cosine 4x. An 1/8 plus a quarter is 3/8. So this is good to go. He's still 1/2 cosine 2x. I've already used him, and so the only thing that's left is plus an 1/8 cosine 4x. And it may not seem like it, but with a certain thing we're going to do in calculus, trying to do it to this thing is near impossible. If you turn it into this thing, it looks more complicated, but doing the thing that I'm talking about, it's called integration, to this is so trivial. As opposed to that, your life is really, really, really rough. But anyway, okay, so remember that. You're definitely going to see something like this, or it might be like sine to the fourth, right, as first power cosines. I might do something like that. Just remember sine squared. So yes, you could write this as 1 minus cosine squared, and then do the 1 minus, this is 1/2 plus 1/2 cosine 2x, which is the same thing as 1 minus 1/2 is still 1/2, minus 1/2 cosine 2x. Or you could just remember that the sine squared gets the minus, the cosine squared gets the plus. And it's real easy to, if you just have this in your head right there, that this is sine squared x and this is cosine squared, that's what you really want to use for the rest of your life. Have that in your head. Okay, so moving on, because we got a lot to do today. So, everybody, any questions on the stuff that we didn't do in person? The stuff that you watched videos on and all that? Any questions? Okay, it's pretty straightforward stuff. And so, okay, let's start here. Can we all agree? So let's say I have a sum. This is the sum. Now, first off, that's what is that? How many?
4.
It works out to 4, right? Now, can we all agree that if I kept doing this, and just kept doing it, that this sum would get arbitrarily large?
Yeah.
Meaning that you give me any number, like 10 to the 10 to the 10 to the billion, right? Some gigantic, stupid, big number. Eventually, if I keep doing this, this sum will get bigger than any number you could imagine. Yeah, okay, good. I want to make sure that we're all on the same page. Because, yeah, I think that's sound, right? That's good reasoning there. That if you kept doing this, it'll get as large as you possibly want. There is no bound on how big it gets. You could also say it blows up. You could also say that this equals infinity. But you have to be careful about how that's used. You could say that if you were to keep going, that equals infinity. But what that means is that it gets arbitrarily large. That it just gets as big as, there's no limit to how big it gets. Okay, can we also agree that this right here, and if I kept on with that pattern, that this would also get arbitrarily large?
Yeah.
Okay. Right. Okay, that makes sense. Now, can we agree that this never settles down on any one value? Because let's just look. What's that sum? If I did that,
0.
0, and then what would that be?
1.
And then what would that be?
So that's always 0.
And so it's always either a 0 or a 1, but it never, as we said before, converges to one value. Right? So this one's blowing up, and so we could say it doesn't converge because it gets bigger and bigger. It never settles down on one value. This gets bigger and bigger. It never settles down on one value. It also blows up. It's not getting bigger and bigger. It's either going to be 1 or a 0, but it also doesn't settle down on one value. So it does not converge to a value. So can we agree on that this will never settle down on one value?
Yeah.
Okay. Okay. Can we agree that this will never settle down on one value? Now, this one's a bit harder to see.
Well, it's still just going to
Yeah,
keep going
still-
back and forth like n.
Yeah, and now, but here's the thing, and you think, well, I'm going to put in I'll put in a 16 here, a positive 16, and then I'll put in a negative 32, and what's really going on here? And so here's the question, and this is kind of what we're getting at. Well, the thing is, if I were to chop it off right there, we have a formula for that, right? And in particular, what I'm talking about is this right here, x plus x squared plus all the way up to, let's say, n minus 1. What is this equal to? This is a formula from last time.
1 minus x to the n over 1 minus x.
Uh-huh. And so it looks like, in this case, the x is what? Here.
Negative 2. Yeah.
Yes, because this is the same thing as negative 2 plus a negative 2 squared plus a negative 2 to the third, and so on and so forth. And so you could kind of see what's happening now. If I plug in a negative 2, it depends whether you have an even or an odd number here. But let's actually do it and see what is the thing for this here. Well, if the x were a negative 2, we have a negative 2 to the n, 1 minus negative 2. 1 minus negative 2 is the same thing as plus a positive 2, right? So that's 1 minus negative 2 to the n. That comes out to 3. And so, yeah, it depends whether n is an even number or an odd number. If it's even, this thing, so negative 2 to an even power, gives you a positive number, but because that's a 2, it gets bigger and bigger, right? And likewise, if this is raised to an odd power, this thing is a negative number, but it's also, as n gets bigger, this thing gets bigger, right? It's going to go 2, 4, 8, 16, 32, 64, and so on, right? And it'll get bigger and bigger. So, yeah, so we kind of have both things happening. It goes from positive to negative for each term that you go. But that's also blowing up, right? Right? Like, plug in a really big number of n, it's either going to be positive or negative, but at any rate, it's going to be a very big number. Like, eventually it'll be, like 256? Plus or minus, who cares, right? I mean, that's not really the point here, what sign it is. The point is, this will get bigger and bigger and bigger, right? And so, this does not converge, okay? Now, okay, 1 second. So, when x, we've seen that when it's in this thing here, right, that we've been trying to wrap our heads around, if x is equal to 1, well, first off, bad luck, right? Bad news. If it is equal to 1, you have divide by 0. But that actually kind of makes sense, right? Because if you're doing this, like more and more, like, well, stop for a second. Let me just say it this way. If x were 1, you wouldn't have tried to do this. It's kind of like you have this formula here, And it works out that x is equal to negative b, blah, 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 all over 2a. And then, like, if a were 0, I'd be dividing by 0. But if a were 0, you never would have done this in the first place, right? So it's kind of like if you were adding 1 here, adding up a bunch of 1s, you'd never would have derived this in the first place. You wouldn't need to. You'd just say, well, how many terms do I have? That's what it is, right? If it's 1 plus 1 plus 1 plus 1 7 times, you'd say, oh, it's 7, right? So we're throwing out 1. This doesn't work if it's 1. This formula works if it's negative 1, but as we're seeing, as n gets larger and larger, it doesn't converge. If n is bigger, if x is bigger than 1, it doesn't converge. We saw that when it was the case where x was 2, right? And I think you believe me that if it were any bigger, it would also not work, right? Adding up a bunch of positive numbers. And we've seen that what happens when it's a negative number that's bigger than 1, or rather a negative number that's less than negative 1, like we had negative 2. Yes, it bounces back and forth, but this guy makes it get bigger and bigger and bigger in magnitude, right? Everybody following what I'm saying thus far? So now here's the question. What happens when x is between, so this is the question, hey buddy, what if x is between negative 1 and 1, and it's strict here? What do you think might happen as n gets larger and larger and larger?
Well, it'll converge to 0. Right.
Yeah, and so this is what I'm asking, is like, what happens to this bit of it as n gets really large if x is between here? And so like, just for instance, right, let's say that x is equal to, a half. And now I want to look at x to the n. Well, that's the same thing as 1/2 to the n, which is the same thing as 1 over 2 to the n, right? And now what happens when I make n really, really, really large? What does it go to?
0.
Yes, as n goes to infinity, this thing right here goes to 0. And that's going to be true whenever the x is strictly between negative 1 and 1. Obviously, it doesn't work if x is equal to 1. Obviously, it doesn't work if x is equal to negative 1, because this either goes to 1 or negative 1. It never calms down. And if it's bigger than 1, right, like 2 to the n, it blows up. But if it's in between here, it should go down to 0 every single time. And I want to just take a minute and prove at least half of this real quick. So my claim is that if this is true, then x to the n goes to 0 as n increases without bound. The bigger you make n, the smaller you make this thing. And what I'm going to do is just start and say, let's look at the case where x is a positive number. And it's strict, and this is key here, is that it's strictly less than 1. Obviously, if it's 0, you're not, again, you're in one of those cases where I wouldn't have used the formula in the first place, right? But here's the idea. I claim that as n gets bigger, well, what could I do? How about I'm going to take this entire inequality and multiply everybody through by x. Okay, is that legit? Can I do that? Yeah. That gives me x squared. And strict here, right, it's strictly less now. And then by assumption, x was less than 1, so I could do this. So this is all true. Now I can play the same game. I can say, well, I can multiply through again by x. And I have x squared times x, x times x, less than 1 times x, which is the same thing as 0, x cubed, x squared, x, which, by assumption, again, was less than 1. And you could see what's going on here. As I could keep doing this over and over and over again, and what we end up with is that we have an xn, we'll have an xn minus 1, and we'll keep going all the way up to x squared. x1, and it is strictly less. And this makes sense, right? Because like, for instance, 0 is less than a half, is less than 1. If I multiply everybody through by 1/2, I get 0. 1/4 is strictly less than a half, which is strictly less than 1. And so on and so forth, right? And so this is what's happening. As long as your x is strictly between these guys, then as you start taking powers of it, it will get less and less. And you could get it as close to 0 as you want. Like for instance, say, like I want to take 1/2 and raise it to a power where it's less than a tenth. Okay, well, 1/2 squared doesn't work because that's a quarter. 1/2 cubed doesn't work because that's an eighth. But 1/2 to the 4th is 1/16, I believe. Is that right? Which is indeed less than a tenth. And you could do that with any number. And so this is what this means here, is that as we make n bigger and bigger, we can make this number as close to 0 as you could possibly want, right? And does everybody believe that that's the case? That you can do that? Now, the negative case is a little bit more tricky. I'm not going to go through it. It's the only reason it's more tricky is that now you have a negative number, and you're multiplying an inequality by a negative number. So like, for instance, if we had -1 is less than -1/2, which is less than 0. Does everybody buy that?
Yeah.
Now I'm going to do the same trick where I multiply everybody through by the x thing. But when I do that, I've just multiplied an inequality by a number, by a negative number. What does that do to the inequality?
It flips all the time.
It flips it around. And so it's not as clean. And so, and indeed, this is true. Because look, -1 times -1/2 is +1/2, which is bigger than negative times a negative, which is a positive, which is a quarter, which is bigger than 0. It's just now you have to worry about the flipping of the signs. And so when you do this, you say, well, -1 times x, x times x. Well, x itself is a negative. And so this has to flip around. And so it's just kind of a pain. Now you have -x is bigger than x squared, is bigger than 0. But that means the same thing as this right here. Right? A negative is a positive. Right? And so I don't want to go into this one. But you can see that the conclusion's also going to work, right? If I multiply this again by -1/2, it'll flip the signs, but everybody will be happy because blah, 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 blah. So that's the idea, okay? So as long as it's strictly between these guys, then, so in other words, if x is between them, here, then this is true. Does everybody buy that? Yeah. Okay, good. Now we can have some fun. This is where it's going to get cool. Because if that's the case, what happens to this as n gets arbitrarily large? So we're assuming, and here's another nifty way of writing this. It'll save me like a quarter of a second. I could just say this right there. So assuming that the absolute value of x is less than 1, that means exactly this. That means exactly the same thing. The absolute value of x is less than 1 means this. Assuming that this is true, then what happens to this bit as n gets arbitrarily large? It goes down to 0. And so we could say then that if you continue this on forever, assuming that this is true, then this is the same thing as that right there. Yeah. And remember, what this means here is like that you could make, as long as n gets big enough, this will get as close to 0 as you could possibly want it. And so this will be as close as you want it to the actual answer, right? So for instance, 1 plus a half plus a quarter, which is a half squared, right? Plus an eighth, which is the same thing as a half cubed, and so on. And so, sorry, I need this little dot ellipsis right there. Okay. That is the same thing as 1 over 1 minus what? What's 1 minus a half? And what's 1 divided by half? How about 2 over 1? How about 2? So you can add up infinitely many things. A really interesting thing about this is that each one of these things is a positive number. And we've just added up infinitely many positive numbers, but that has converged to a value 2. That's pretty cool. And also from this right here, we could see that whenever this isn't true, if you try to do this, it's going to blow up and you're going to get junk, right? So if I had this, 1 plus 2 plus 2 squared plus 2 to the third, and so on, you could say this does not converge. This does not converge. This blows up. And so we could say that this sum does not exist. That's another way of saying this. Like, compute the sum if it exists. And that you'll see that a lot. So in this case, this sum does exist. It does converge to a value. This one does not, because this is the same thing as 2 to the n, 1 minus 2, as n blows up. If n blows up, 2 blows up. Whereas in this case, this is the same thing as 1/2 to the n. As n gets really, really large, then this thing goes to 0, which gives us that. Everybody follow that?
So do all sums like this, where x is less than 1, converge to a certain number?
Every time this is true, every single time this is true, then this is true right here. Every single time. And you could plug in any number. And so one way that we write this, did I write this here? Yep. So, in other words, what this means, a way of writing this is this thing right here, that this thing that goes on forever is, well, this first one right here was the sum as k goes from 0 up to, well, I guess n minus 1, but whatever, x to the k, right? That right there is 1 plus, right? Because k, when it's 0, it's x to the 0 is 1, and then it's x to the 1, x to the 2, all the way up to x to the n. And now what we're doing is saying, well, let's not stop at n. What does that mean? Well, what we're doing, and in calculus we'll do this rigorously, the limit as n goes to infinity. And that's what we're talking about here. We're saying, let's just keep going. Let's just never stop. What happens when we never stop? Well, if the absolute value of x is less than 1, then the limit of this, because this is what we know, this is the same thing as 1 minus x to the n over 1 minus x, and then we take the limit. We see what happens as n goes to infinity. And if this is true, then this is perfectly well defined. This limit exists. This converges to a number, and that number happens to be 1 over 1 minus x. And in that case, if this does work, then we write it this way. We say the sum as k is from 0 to infinity of x to the k, which is 1 plus x squared plus, goes on forever, which is 1 over 1 minus x. Cool, huh?
Yeah. It's pretty cool.
And so that's what that means. It's not like we're not plugging in an infinity here. It just means that if this works, which always works if the absolute value of x is less than 1, if that's true, then this is perfectly well defined, and you could do this. You could let n get really big, and that makes this thing go to 0, which gives you this right here. Now here's something. I do want to say this. Another thing we could have done from the very beginning is say, well, let's suppose that we had this and it went on forever. Let's call it y. Let's just pretend for a second that it does converge to an actual number. It doesn't blow up, that it actually gives you a number. And we'll call that number y. Well, one thing you could do is this. You could say, well, that's the same thing as this. But I could factor out an x from there. But isn't that? same thing, right? And so 1 plus x times, instead of all of this, we said at the very beginning, that thing is equal to the number we're trying to find, which is y. So we have this right here. I'll just do it right here and say, well, if y is equal to 1 plus xy, then I could bring my xy over, minus xy equals 1. Factor out of y, 1 minus x. And as long as x isn't equal to 1, we get y equals 1 over 1 minus x. Now, the reason we didn't start with that, so this is what we found, is if we did start there, then the only thing we'd realize is, well, if you divide by 0, you're bad, so x cannot equal 1. And then you go and try to plug this in, and you're like, okay then, 1 plus 2 plus 4 plus 8, that should be the same thing as 1 over 1 minus 2, which is 1 over negative 1, which is negative 1. Does that make sense? No. And the problem is, like, so you're like, well, where did this break down? And if all you're looking at is this right here, this work that you've done and this work over here, blah, 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 if that's all you were looking at, it would be really hard to find out where this broke down. Until you realize, well, that doesn't make any sense. Like, you can't, like, if you're assuming this works, but then trying to find, well, for what values does it work? You can't really figure that out easily. The only value that you figure out doesn't work is 1 itself, because of that. But this method right here gave us the analysis we did earlier, where we could say, look at that. This is what happens as n gets really large. It's all focused right here. And then we wrap our minds around that, and then we can come up with something that actually does work. And so this is called an infinite geometric series. Geometric because it's doing the thing, right? You're multiplying by this. Each term gets multiplied by the same ratio or whatever every time. Series. So series means infinite sum. And in general, if you have an infinite sequence, starting at 1 or 0 or whatever, it doesn't matter, then if you do this type of thing. So we're assuming that you have an infinite sequence a sub n, and you're saying add it up. This thing, if you're adding up infinitely many terms, this is called a series. So it's redundant to call it an infinite series, but half the time you'll hear me say infinite series. Like, you'll hear everybody, it's just one of those things you say, it's infinite series. Well, yeah, that's what a series is. Every series is infinite. And so, this is a series. And, yeah, I did want to say that. A big topic in analysis is, given some series, does it converge or not? It's a huge topic in analysis, which, as I've said before, is what you do after advanced calculus. And it's more of a rigorous footing for all of this stuff. Because right now, you might say, well, hold up. I mean, like, come on, really? Like, can you justify this a bit more than, well, look, you get smaller, and so you're good, and you can do this. That's what analysis is all about. Is like, let's make this as rigorous as we possibly can. And a big topic in analysis is when does this actually converge to a number? When does it not? Under what circumstances can we do certain things to a series? Etc., etc. So, any questions? Now it's time to talk about how are we going to use this fact. Okay. So we already did 1 plus a half plus a quarter plus an eighth, and we saw that that comes out to 2. But you could do that with anything, just so long as this thing, that the x in absolute value is less than 1. And so here's an example of when x is less than 1. How about a third? How about a ninth? How about a 27th? And so on. And so how could I rewrite this as something plus something squared plus something cubed plus and so on?
Just put 1/3 there.
It's a third, right? That's very easy in this case, right?
The first one's 1, it's pretty easy.
If the first one's 1, it's pretty easy, unless, as we're going to see later, it might not start at 1. And that part might have nothing to do with this part. And so you might need to factor a couple things out and whatnot. Yeah, but usually you could look at it. Usually if it's 1 and then it's that, and as long as you square that and get that, you're good to go. But sometimes it's not. Like if this were a 7, then you need to work with this part right here and say, well, I need to factor something out, blah, 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 blah. That's not the idea. Okay, well now here's the question. Is the absolute value of 1/3 less than 1? Okay, then we could use this, or we could take the limit and we get 1, that this should be equal to what? 1 over 1, what?
1 minus 1/3.
Yeah.
1, that's what I'm getting at, yeah. Which is the same thing as 1 over what?
2/3. Which is 3/2.
Which is 3/2. Nice, so this equals 3/2. Which is to say that you keep going, you put as many terms as you want. You add this up till you have 1,000,000 terms, and it will be very, very, very close to 3/2. It's not going to start bouncing around after 3/2, you know, or something like that. You add in another term, it'll get even closer. You add in another term, it'll get even closer, right? And that's the idea. That's what all of this means here. Okay, here's a trickier one.
So it's just -1/3.
Yeah, it's just plus -1/3 plus -1/3 squared plus and so on, which is the same thing as what?
1 over 1.
Over 1 minus.
Wait, are you sure what happened? What happened to this part?
It's 0.
It works out to 0, and that's because the absolute value. See, that absolute value is nice, right? That thing is less than 1 right there, and so 1. What am I writing?
Minus 1/3.
Minus a third, which is
4/3.
there you go. That's the same as 4/3, which is 3/4. There we go. That actually makes sense. Because remember, when it was all positive, when it was 1 plus a third plus a ninth,
Oh,
and so
it's
on,
half.
it came out to
yeah.
3/2. Interesting. So you end up taking out about half of it.
Yeah.
Exactly half.
Exactly half? About. Maybe. Yeah. And so that's cool. Okay, so that's nice. Really, and this is all coming back to this thing. And it really, if you just remember this, and you have something, you could just say, well, wait a second. This is, you know, like, you have some kind of series that you're working on. 2 plus, I don't know, 9 plus... why did I do that? Why would I do that to myself? 2 plus 4 plus 8. And you say, well, wait a second, hold up. It looks like this is a 1 plus a 2 plus a 4. Oh, what was the thing? What did it have to... Well, if you just remember this, you could say this is the same thing as 2 times 1 minus, I guess it's 2 is getting squared each time, so 2 to the n over 1 minus 2. And then you just ask yourself, can I go on forever? No, because 2 raised to a power, or -2 raised to a power, right? If there were minuses between them, blah, 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 blah. Like, in either rate, like, in any case, this is what this all comes from. And if it is the case that this were a half, yeah, there you go. Nice. That was great. And so if this were the case, and you'd say, well, wait a second, is a half... Yeah, I could take a half. I'm sorry. But you get my point, right? Like, then as n gets really big, this goes to 0, and so there's your answer, right? Okay. Your book has it, and like I said last time, I don't like to think about it in this way, but assuming that this is a geometric sequence, and it starts at 1, and you're going up to infinity, then this is the same thing as a 1 times 1 minus a 1 or whatever. No, it's whatever the ratio is. I'm sorry. It's whatever that ratio was. All right, that's how they do. I don't like to do it that way. And again, I'm not even right. I don't. Yeah, because this is the A1 plus A1R plus A2R squared. Oh no, A1 every time. Yeah. A1R cubed and so forth. And so you factor out the A1, which is how I prefer to do it in the first place, right? And saying, well, as long as the absolute value of R is less than 1, then we could make this jump where we say, well, 1 over 1 minus R. And that's where that comes from. I don't like to think about it like that. I like to think about it like this. That will help you more in the future than memorizing 2 or 3 formulas that look like this. Okay, so it's like, well, what do I do with the A1? Well, just write it out and get it so that it's 1 plus some stuff, and then just use this. That's how I prefer to do it. If you want to do it the other way, go ahead and memorize a bunch of formulas. That's fine with me. That is cool. So, okay, now, let's use this. This is cool. So I didn't assign this one, but you'll probably want to know how to do ones like this. A ball is dropped from 60 feet. It rebounds. In other words, it bounces back up. It rebounds to 2/3 of the initial height.
Oh wait.
And it will keep getting
After each drop,
cut. 30, no.
each bounce or drop or whatever. I wrote it as drop, but you know what I mean. Okay. Approximate the total distance traveled.
Oh. So just add them all. I'll add them all.
So I suggest you draw this out, because this is, if you just think, well, I have this formula, an A1 and 1 minus 1 over R, you're going to mess this. I guarantee you're going to mess this up. Every student who's come to me with a problem with one of these has messed it up because they tried to plug it into a formula. And I say, draw it out. They're like, I don't like to draw it out. I'm like, okay, well, I have a hard time. This is not hard. Because what I'm going to do is say, okay, you drop a ball from 60 feet. So it starts here. There's your ball. And it drops. I'm going to make this a bit bigger. This drops 60 feet. Now it says that it rebounds back up to 2/3. Now I could say, okay, well, what's 2/3 of 60? I could do that. And I don't care. I don't care. I'm going to go, this is what I'm going to do. Whatever it is, it's 60 times 2/3, isn't it? Like, that's how you would find it. You would take 2/3 and multiply it by that. It's what?
40.
Okay, great. Good for you. Now, now it's going to drop back, isn't it? It's going to drop back down the same distance.
Yeah.
This is where it's tricky. It's the same distance. It's still 60 times. But now it's bounced again.
It'll be 2/3 of.
And it'll be 2/3 of that. So we take whatever distance that is and multiply it by 2/3, which is 60 times 2/3 times 2/3.
Or 9.
Or how about, but let's not write it like that.
Oh, yeah. 2/3.
Why not 2/3 squared? Because you know that your goal is, if I could write this as something plus something squared plus something cubed, and so we're going to go ahead and keep it like that. Now it drops the same distance, 60 2/3 squared. Now it comes up to 1/3 of that, another 2/3 of that, which is, how would you get it? Well, you take that number and you multiply it again by 2/3 for a total of 60 times 2/3 cubed, and so on and so forth. Now all we need to do,
And it bounces forever.
and it bounces forever, or does it? Or does it? And that's a question we could get into, not today, but it's in the book too. It even says that, I'll tell you, on page, if you're interested, on page 813, the discussion exercises number 7 on 813.
Well, if it's like there's
You can
no
figure out,
friction-
does it bounce forever?
If there's no friction and no.
Well, anyway, just
Wait.
do that question and see if it does bounce forever. Okay, so let's just add all of these up.
Well, each one is repeated twice. So
Is every single one of them
Except
repeated
the first
twice?
No, except the first. So
And that's what I was getting at when I was like, sometimes you'll have a 7 plus 2 plus a half plus, in which case, this is one of those cases where this is going to mess us up if we're not careful, is that you have 160. Now, how many of these do you have?
2.
Okay, plus 2 times
2/3.
60 times 2/3. Is that right? Have I counted for all of them? If I go 2 times this much, that is that one term. Now I'm going to add it to this guy, which is 2 times 60 times, what is it?
2/3 squared.
Let's just write that as 100.
Squared. You could, yeah, and you could say 120 for each one of these, and that would be perfectly fine. I'm going to just do it this way. And so now, of course, now there's 2 of these, and so the rest of them have this form where they go cubed and so on and so forth and so forth. But now what I need is 1 plus something squared, and I'm almost, you see,
Factor out a 60 and then you'll be able to...
yeah, but then you have that 2.
So factor out a 120 from all of them except the 60. So,
Wait.
So like, group
What
it
I
to
suggest.
60 plus 120 times.
What I suggest is let's forget about that first term.
Yeah.
Let's just look at this term. And then let's just factor out that whole thing right there. So I'm going to keep this over here. Plus, I'm going to factor all of that stuff out of the first term to give me a 1. So when I factor it out, I have 2 times 60 times 2/3.
Yeah.
Now what's left here?
2/3.
Just
Yeah,
2/3.
And
Yeah.
then 2/3.
Oops. Just 2/3. And then
2/3 squared.
2/3 squared. Now there are other ways of doing it. There are definitely other ways of doing it, and especially with that formula with the A1. Oh, there's your A1. Yeah, but I like to do it this way because now I can say, aha, 2/3 is less. It's in between -1 and 1. And so I could use my result from earlier. That's 2 times 60 times 2/3. Now this works out to be what?
1 over
1
1
over
over 1
minus 2/3.
minus 2/3. Now let's just work that out over here. 1 over 1 minus 2/3 is 1 over how many thirds?
1/3.
No, 1.
No, 1 over 1/3.
1 over a third, which is 3. So, we get
Oh, that cancels out.
60 plus 2 times 60 times 2/3 times 3. Right? All that worked out to 3. The 3's cancel. 2 times 2 times 60.
It's 4 times 60, so
240 plus 60.
yeah, 240.
240 plus 60
300.
is 300 feet. There you go. There's your answer. I think that's really cool. I love questions like this. Yeah, and then the question was, wouldn't that take an infinite amount of time? I want to check out that thing I recommended to you. This is kind of like the Achilles problem, right? Achilles is trying to catch a tortoise. You guys know about this? This is Zeno's paradox.
Zeno's
Thank you.
paradox.
Zeno's paradox,
Yeah,
right?
we did that
So
last.
there are 2. Achilles is 2 units away from a tortoise.
Oh, and you can.
And here's Achilles. And Zeno's paradox is like, well, it takes him some, like, eventually he gets to half the distance. And then he gets to half that distance. And this right here is a half. And then eventually he gets to half that distance, which is a quarter of a unit. And then he gets to half that distance, which is an eighth of a unit. And Zeno's like, well, he'll never get there because he always has to travel infinitely many. He has to chop this up in infinitely many times.
I'll never get anywhere.
He'll never. So you can never move anywhere, but we can see that you can move places. So what's going on? Well, how much total distance has he moved, and how much time does it take to do this? I would suggest that you play with that question.
What question number was it?
So it was on page.
813, number
You
7.
said 813, number 7.
Yeah.
Just make sure that's the one. Yep, 813, number 7. It says rebounding ball. Only instead of talking about the height, you're adding up the heights. Now you're going to add up the times. Because how long does it take for the ball to get from one to the other? And it's the same kind of thing. It doesn't take as long for the ball.
Oh, because the time.
It only, now that the ball is saying going 1/2, it only takes half the time for the ball to drop that far. Now the ball's going there, it only takes 1/4 of the time for the ball to drop that far, and that's the answer to the paradox. So, okay, here's number 32. This is, oh, and you guys got the homework? This was 27 to 45. Did you guys both get it written down?
Yep.
So I don't have to rewrite that? Okay, cool. Number 32. Find the sum of the series if it exists. So for instance, if 32 said this, 1 plus 4 plus 16 plus, and so on, does that sum exist?
No.
No, it blows up. Right, so no, it does not exist. So we can say it diverges, it doesn't converge, blows up, goes to infinity, the sum does not exist. But what about this one? This is not so bad. 2 plus 2/3 plus 2/9 plus 2/27, and so on.
You can factor out 2.
Factor out 2, leaving you
1 plus 1/3 plus 1/9, which we already did. Equals.
right. And so we already did this. This is the same thing as, let's practice this. What does this work out to?
1 over 1 plus 1 minus 1. Thank you.
Which is the same thing as 2, 1 over how many thirds?
2 over 3.
Oh.
Which is 2 times 3
Yeah.
halves, which is 3.
Which is 3. Nice. Okay, so that sum does exist, or that series does converge. The sum does exist. A lot of different ways of saying the same thing. The series converges. It settles down on one number. And really what we're talking about, what is it that is converging? Well, it's the partial sums of the series. Remember we have this Sn is equal to 1 plus x plus all the way up to xn, which we said is 1 minus x to the n plus 1 over 1 minus x. And so as you start doing this sum, you have S1, then you can take S2. So in other words, you're adding up successively. And what you're looking at is, does this sequence converge to a number? And it will, as long as absolute value of x is less than 1. It will get closer and closer to 1 value. But anyway, okay. All right, a few more minutes. We're right on time. So, number 38, same question. Find the sum if it exists. And this one's really ugly. 250 minus 100 plus 40 minus 16 plus, and so on. What? So, there's a couple ways we could go about doing this. One thing you could do is factor out a 250 to get a 1 in the front. And if that's the case, then each one of these, as you factor out a 250, you'll end up with something over something, like an a over b, and hopefully what you'll end up with is an a over b squared here. And then hopefully what you'll end up with is an a over b cubed here. That's kind of a pain. For at least for me, but one thing we do know is that if this is a geometric series, which hopefully it will be, is that you could just take the next one and divide by the first one to find the ratio.
Yeah.
Right. So I could say, what's 100 divided by 250? And it's like not just 100, it's a negative 100. Yeah. And so that's the same thing as negative 10 over 25.
Negative 2/5.
Negative 2/5. And so now, here's the thing, that like hopefully I could rewrite this as something and then with the 2/5. And now that I've figured that out, I might just go for it. I'm just going to factor out that 250 and just see if this is what happens. So I'm thinking, okay, we have my negative 2/5 here. And hopefully when I factor out that 250, that leaves me a 1. And now it's a negative, so we should have a minus 2/5 plus 2/5 squared minus 2/5 to the third plus, and so on. And let's just check and see if that's the case. 250 comes in, yeah, by design. 250 comes in. This is minus 250 times 2 over 5. 250 divided by 5 is 5. Wait, yes. So 50. So that's 50 times 2 is 100.
Yeah.
Nice. I'm going to check one more just to make sure that I haven't messed this up. So the cool thing is, like, we're in a section called geometric sequences. And it's like if I didn't know that this was possibly actually, anytime you're given something like this, that's the first thing you want to check, because if it is geometric, it's going to be so easy for you. But now I'm going to check one more time, and I'm going to see what happens when I bring that 250 into here, and I multiply it by this, which comes out to 4 times over 25. Okay, so I have 250 over 25 times 4 on the top. This should work out to 10, right? 250 divided by 25 is 10. And so now I have 10 times 4 is 40. Does that work?
Yeah.
Yeah, okay, so I feel good. I'm ready to go. So a few different ways you could do it. This is one of those where the actual formula in the book does work pretty well, but I prefer to do it this way so that I know what I'm doing. Now I ask myself, wait, is this going to converge?
Yes.
Yeah, why?
Because it's less than 1.
Because the absolute value of, ooh, and look what I did, I did not do, ooh, you gotta be so careful for that. Make sure, I almost just plugged in a positive 2/5 into everything. It's not positive 2/5, it's negative, right? Because you have that alternating thing. And so, the absolute value of negative 2/5 is indeed less than 1. And so, we could rewrite this entire series as
1 over 1 minus negative 2.
negative 2/5. You see, if I had that positive 2/5 in there, that would not be the
Which
right.
is 7.
Which is how many? 1 over 7/5. Which is 250 times 5/7. We're done. I don't care what that is. That's fine. That's good.
How many do you think it reduces?
Yeah.
Unless 250 is a multiple
Divided
of
by
7.
7.
I don't think it is.
Yeah.
No, because it's 10 times 25. So nope. All right. Everybody got that?
Yeah.
Okay. A couple more things. Okay, we gotta go quick because I do want to get to this last thing. Oh man. Okay, so this is what I think. This is one of the coolest things. Here's number 44. This is such a cool application of this. Write as a rational number. In other words, write as an integer divided by an integer. And what it is 3.2394, and the 394 is repeating. What? So this is what I'm going to suggest we do.
So it's 3.2 plus 0.0394 plus.
Yeah, exactly. So what I'm going to do is rewrite this as 3.2 plus 0.0394 plus, now we have how many zeros? 1, 2, 3, 4, and then a 394. So 0.1234, 394 plus, and so on. I'm going to do one more, okay? So 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros, 3, 9, 4, and so on. Now, the book does it a certain way that I hate. I much rather write these as rational numbers, write them as fractions. So like for instance, 3.2 is 32 over 10. You'll notice that's, like this could have been a 7 and a 5 and it has nothing to do with what you're about to do, right? Like the bread and butter is going to happen right here. This is the geometric part. No matter what this is, it really doesn't matter. Forget about it until later. Now I want to rewrite this as 394 divided by what?
1,000. No, 100.
Let's see. How many zeros should you have? You should have the same number of zeros as you have decimal places, right?
Yeah.
Because look, one decimal place, 1 0. If it were
Yeah.
2 decimal places, you would need 2 zeros. And so that's an easy way of doing it. You just count the decimal places. 1, 2, 3, 4. You should have 1 and then 1, 2, 3, 4 zeros. Here you have how many decimal places? 1, 2, 3, 4, 5, 6, 7. So you have 1, 2, 3, 4, 5, 6, 7 zeros, and so on and so forth. And I do want to do one more. We're going to go 394 over 10 to the... And actually, what you could do is you could just say, well, wait a second. How many zeros is this?
4.
4 zeros. So I could just write that as 10 to the 4, right?
Yeah.
How many zeros was this?
7.
So I could just write that as 10 to the 7. How many zeros is this? Well, we know it was 7.
Plus 3.
And then 8, 9, 10 is plus 3, right?
plus
So
3.
to the 10.
Yeah, 10 to the n plus 3.
And so...
For the,
Yeah, well, hold up. Now what we want to... Yeah, each time you're going to pick up 3 more because that's the repeating part, right? It's 3 here, so that's how many zeros you need. That's how many extra ones you're going to have. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But what we're trying to do here is say 32 over 10. We need a 1. So I'm going to factor this whole thing out. I'm going to say 394 over 10 to the 4. Leaving me a 1. Plus, 394 is gone. What's left over down here?
10 to the 3.
10 to the 3. Plus 1 over 10 to the
6.
6. Or in other words, that's the same thing as
1 over 10 to the 6.
10 to the 3 squared. And it
yeah.
better be, right? That's why I brought that one in there. Because I did not want to mess that up. I wanted to make sure that I do have the formula right. Okay?
So it's 1 over 1 minus.
And so, yes, 32 tenths plus 394 over 10 to the 4. 1 over what?
1 minus 10. 1 over 10 to the 3rd.
And in this case, I'm going to bring it up that way. Because now we have 1,000 over 1,000 minus 1 over 1,000.
199.
Yeah, so 32 over 10 plus 394 over 10 to the 4. Now this is 1 over 999 over 1,000. Or how about 1,000 over 999? 1,000 is 10 to the 3.
Oh, so that's
999. So that's times 10 to the 3 over 999. I'm going to go back way up here and say that's the same thing as 32 tenths plus. Now here, we could cancel one of these guys, right? So there's 110 left over. So 394, 110 times 999. Now if we need a common denominator, I could
Multiply top and
say
bottom.
multiply the top and the bottom by 999. And that common denominator is 999 with an extra 0 on it. Now, I don't care about this. If you want to leave this as 999 times 32, that's cool. Plus 394, that's cool. That's perfectly good. Now, if you want to check it in the back of the book, they probably do this and then reduce it and stuff like that. But that is an integer divided by another integer. We are good to go. Okay? Just make sure that that doesn't look like a thing. And you'll notice that 99999, etc. does show up in all of these. It's always going to be the case. Okay. Now, I gave you number 63. I'm not going to talk about 63, but I'm going to talk about something similar to it. Like a similar mathematical object. And I know we're over time by a little bit, but I do want to get into this.
So is it like an extra hard problem? Like,
Not that hard, but you need to, I want to give you an idea of how you might want to go about doing this. There's something called the Cantor middle thirds set, named after Georg Cantor. Yeah, Cantor set, but Cantor, the Cantor set. And there's a bunch of different Cantor sets. One of them is the middle thirds Cantor set, which is you take the interval from 0 to 1, and we're imagining this is on the real number line. And what you do is you delete the middle third. So you have 1/3 here, 2/3 here. And what we're going to do is we're going to take out the open interval from 1/3 to 2/3. Now that leaves that point there, and it leaves that point there. So you're left with 2/3. included brackets right there. Okay, so that's the first iteration. You start with the thing, and then now n equals 1, or I mean, you could call it n equals 0. You could call it n equals 2. Who cares? The idea is that's the first step. Second step, you have these guys left over.
Take out the.
And so you take out the middle third of these guys. Now we have this right here. There you go. Now, the next step, you delete this middle third, and so on and so forth. And you do this to infinity.
That's no area.
Well, a line doesn't have area to begin with. But a line has length.
But it has no line.
And so here's my question. Is after you've done this to infinity, what is the length of the contour set?
0.
Prove it.
Because any segment you pick will be removed eventually. Right?
Nope. Turns out that there are parts that aren't. Like, you might think, so 1/3 is always going to be here.
I guess, yeah. Because
Right? 1/3 is in the contour set. 2/3 is in the contour set. You'll never remove it, right? You'll remove that part, leaving you this little bit.
But it's
1/3 is an endpoint.
So does it,
Then you'll remove that middle third, and so on and so forth, but 1/3 is still there. Then you'll remove, but 1/3 will always be there. 2/3 will always be there. I believe this was 1/9. It will always be there. This was 1/27. It will always be there, right?
Infinite points that will
Points
always
that way.
be
There are
there.
infinitely many points that will always be there, but not just the end points. It turns out, this is really weird. We can't get into this right now, but 1/4 is not an end point, but it is in there.
What?
Yeah.
1/4.
1/4 is never removed. After you've done this infinitely many times and you've deleted infinitely many middle thirds, 1/4 is still in there, and it was never an end point. What? What? Weird. So, I don't buy, like you tell me that the length is 0. I don't buy it because of that weird fact that 1/4 is in there. I'm willing to believe that,
Can you prove it?
well, that's what I'm going to do. What we're going to do. What is the, I can't spell, length of the contour set? I mean like the total length, because obviously you split it in half, you're like, whoa, but, okay, so this is what we're going to do. It turns out, Victor's right. The length is 0, but we need to show that that's the case. And so this is how we're going to do it. We're going to start off.
Infinite endpoints is still 0 because infinite points is still 0 because 1 point is.
Yeah, and so like let's see, here's my set. It's 1/2 and pi. What's the length of that? Well, it's not that none of them are between there. It's just this 1 point and this 1 point. What's the length of a point? 0.
0.
So what's 0 plus 0?
Yeah, 0.
Okay. So, but the interesting thing is, like, you think, and it turns out I think it is totally disconnected, that there are no 2 points that are together, but somehow a
Because
quarter.
if there were, then there would be.
I could show you how, but I don't have time.
If there were 2 points next to each other, then it would have length, right?
How many? Here's an even better
What,
question.
what's next?
How
to
many
each-
points? How many points are still in the set?
Infinite.
Yeah, all the multiples, 1/3 to.
Are there less
X, I
points
guess.
after you've taken out after you've done this? Are there less points than what you began with?
Yeah.
Well, it's infinite either way.
So here we go. Watch. So the length, starting off, the length of the contour set. Well, it's 0, right? But here. So here's the length of this thing. The length is 1. Yeah.
Yes.
Okay.
Yes.
Now on the second iteration, we've dropped out the middle third,
2 times.
and so now this length is it was 1,
Now it's 2.
but now you've minused off how much?
1/3.
A third. Okay.
Oh.
Now, in this next iteration, it was what it was previously. You started off with this much. 1 minus a third is how much you had. But now, how much have you dropped out?
1 minus.
1 minus
1/3.
1/3 times a third.
Whoa,
Times two.
Wait,
Wait.
minus 1/3
Whoa.
squared.
Well,
yeah,
hold
yeah,
up.
yeah.
How much is this? Because this is what you've deleted.
That's
That's a 9th.
This is 1/9, and how many of them have you pulled out? Ah,
We can
1
use the formula
minus
for this,
2/9. Or how about, because how did you find out that that was a 1/9? You said, well, if that's a
Yeah.
third, and I take a third of it, it's a third of a third, so how about minus 2
Yeah.
thirds, so 3 squared. Now, one more time. Now, you had this, and what you're going to do is delete this middle third right there. You delete, so this has been taken out from there to there. You pull out this middle third. This one gets deleted from in here. This one gets deleted from in here. So what's the length of each one of these that has been deleted?
27th.
It's
so
what?
3 to the 3rd.
Oh yeah, so the length of the thing. And how many things are there?
8.
You're pulling one out of here. Wait. You're pulling
4.
one out of here. 2,
Oh.
3, 4. So it's 4.
Which is 2 squared.
Yeah, that's how you want to do this. So you're minusing off 2 squared
Over
3
Yeah,
thirds.
okay.
Minus 2 thirds
3 4.
3 fourths. Because in the next one, you're going to have a total of 8 bits that you're pulling out. And each one of them will be 1/3 less than the first one. And so now, okay, now here we go. And going on and on forever. But now we need to compute this. And you'll notice that this is not, like I said, sometimes you want to ignore this 1 right there.
Yeah.
Because this is not, I'm not just squaring a third each time, am I?
No.
So I'm going to go 1 minus a bunch of junk. And why don't I factor out that minus 1/3 from the front?
Yeah.
To give me a 1. And then what is this?
1/3.
Is it plus?
Oh no.
Is it plus or minus first off?
Minus. And then.
Wait, I factored out
Oh, you
the
factored
minus.
out. So plus
So plus what?
2/3.
2/3, because I'm leaving that 2 in there. What about this one? What's left over? This is, first off, is it plus or minus?
Minus. No, plus. Yeah. And then it's 4 over 3 squared. So 2 squared over 3 squared.
So how about 2 over 3 squared?
Yeah.
Oh.
Yeah, right.
Okay.
Right, and that's yeah, because you've pulled out 1/3. You pull out the negative. You pulled out one of the 3's from the denominator. You're left with 2 over 2 to the 2, 3 to the 2, or you could write it like this and make your life easier. And that's the whole point, right? So now, what we're getting here is when you take this limit, when you do this to infinity, then the total length of the contour set will be 1 minus everything that you just took out, which is 1/3.
Times 1 over.
Now, can we do, is this legit? Is
Yeah,
2/3?
it's less than
Yeah.
Okay, so 1 over
1 minus 2/3.
Yeah.
2/3, which is the same thing as 1 over what?
0.
1 over what?
Alright, 1 minus
1 bit at a time, man. I'm not as fast as you. So it's, what is this?
1/3.
1/3. When, what is that? So that's 1 minus 1/3 times what?
3. Which is
1 minus what?
1.
Which is? Your intuition is right, but I didn't believe you because I happen to know this weird fact that it's not just the endpoints that stay in here. I could show you that some other time. But it's not just the endpoints. But if you said, well, if only the endpoints, then I could see they'll get infinitely disconnected and there's no length there. But there's this weird fact that there are points in there that aren't endpoints. So that makes me think, well, maybe there's an interval left over. Maybe something weird happens, and because you're deleting, I don't know, but maybe somehow an interval gets left over, and then maybe it has some positive length. Maybe it's like, a billionth of a billionth, but maybe it's in there. Turns out, no, it's 0. But so this kind of thing that we just did, this kind of reasoning where we had to say, well, hold up, where's this, and there's this, and there's this, pull this out and figure this stuff out. This is the kind of thing you're going to need to do for 63. It's not as intense. I don't think they ask you to do it to infinity, which they should. It would be like, just keep doing this, and what would the final answer be? But they don't. So anyway, that's all I got. We've run way over time. Any last minute questions?
I don't think so.
All right, guys, have a good one.